Cool. Did any questions come up during the break that you still want to discuss? Okay. Otherwise, we have to talk about optimizing the objective in practice. So before the break, we derived the elbow objective, which is the which had this reconstruction term and the KL regularizer, and then we averaged that over the training data, and that's a lower bound, so we try to maximize it because we want to maximize the likelihood. But then, as we also already learned, most of these packages normally minimize something, so you take the negative later on of that, so that's minus the loss function that we're going to minimize later on. Let's look at these two terms if we want to practically optimize them. So the right-hand term is the KL regularizer, and if the two distributions, the prior and the posterior, are Gaussian, then there actually exists a closed form solution for this KL divergence. It's just an expression that you can implement, and then you can backpropagate into that, and that's completely fine. If you have a different expression, or if you move to hierarchical models, then suddenly you can't compute this KL divergence in closed form anymore, and then you have to estimate it using sampling. And we'll talk about that in a minute. And then on the left-hand side, you have the reconstruction term, where we draw a sample, or where we take an expectation over the posterior approximation, and then we evaluate it at the likelihood. And the likelihood was this nonlinear function that introduced all of the problems in the first place. And we still can't compute an expectation over this thing, even if we're computing it over a Gaussian, because otherwise we would have been able to solve we wouldn't need variational inference. So there's no closed form expression. And then what people do instead of is that they estimate this using samples. And the main difference to the thing that we saw earlier is now the expectation here is on the outside of the logarithm, which is a sum of logarithms, which is fine. Whereas earlier we had this expectation inside the logarithm. And expectations inside a logarithm or some logs of sums are something you don't want to think about. And so this you can now estimate in an unbiased way using Monte Carlo samples. And typically, and we'll get to this, people will only use a single sample for this. And in practice, we also then have to use mini-batching because not the entire training set fits into the memory. And so we need to use stochastic optimization on top of this as well. And then if we think about it, we have two sets of parameters now that we need to optimize. One are the model parameters, theta, so we need to compute gradients with respect to that. And then we also need to compute gradients for the inference network because we need to find this network that predicts the approximate posterior for us. And this is where the whole field of gradient estimation that I've worked in quite a bit comes in. And I didn't want to put the very heavy maths on you, but I thought I should give you a very quick primer of kind of the background behind the reparameterization trick to give you kind of a bit of an understanding of that. So in practice, we can't evaluate these gradients because of this expectation here, because we can't compute that exactly. And so we have to use Monte Carlo sampling in order to do that. And what does Monte Carlo sampling mean? So here I have this problematic term that we can't evaluate exactly. But what you can do is you can draw a sample from Q. It's just a single sample. So instead of using the expectation, you just say I'm going to approximate by a single sample estimate. So I'm going to use a single sample that I draw from the approximate posterior. I'm going to plug it in here. Then I'm going to say that's the value. And obviously that value can be very large, can be very small, but in expectation, it will be the thing on the left-hand side because it's the expectation, which is the nice thing. But in principle, this can have very, very large variance. But we find that often in machine learning, it's actually quite good to do this, or it's sufficient to do this. In some cases, you have to use more samples, but in VAEs, typically a single sample is enough. And this is an example of an estimator. So the thing on the right is an estimator that estimates the expectation on the left. And then when you have an estimator like that, you can ask two questions. You can ask, is it unbiased? So does it actually approximate the quantity that I'm interested in? And I just told you if I take many samples, it's like taking an expectation, and the expectation is the thing on the left, so we're good there. And then you can ask, what's the variance? How large is the spread of this? And that is something that sometimes you can approximate or think about, but often it's something that you find empirically, and then the variance is too large, then the model doesn't train. and then you use 2 samples, and then it doesn't work, and then you use 10 samples, and at some point it starts working. So that's kind of the magic of another hyperparameter in deep learning that you have to play around with, but you can usually start with one, and in many use cases that's enough. And now this kind of reparameterization trick that people have already talked about comes in, because the problem is the expectation measure depends on the variable we try to take gradients with respect to. So if we, like this is on the left is one term of the elbow that we try to take a gradient of, and now we say we approximate this expectation by a single sample estimate. And we take the gradient with respect to these parameters phi. So here we want to take gradients with respect to the thing that's here. But now you've sampled this thing, and you somehow need to take gradients with respect to that one sample. And sampling is something very discrete because you can't have half a sample. So it's like, how do you do that? What should you do with this? And that's where like a small question for you comes in, which is if I have a Gaussian distribution with some mean vector mu and some scale sigma, and you want to implement this in code, then typically in code, there isn't a function where you can tell it, or like at least in MATLAB, which is what I grew up. I think nowadays all of the things do everything for you, but in the old days where you had to compute the gradients by hand, you also had to do this yourself. And you had access to like drawing random variables that can be distributed according to a normal distribution with 0 mean and scale 1, which is the standard Gaussian. So that is something that MATLAB or NumPy can give you. But MATLAB and NumPy can't give you samples from a distribution with a particular mean and a particular scale. And my question to you is how can you use the sample that you get from sampling a standard normal and massage it so that you get a sample that comes from this? So how would you do that? Think a little bit about it, talk to your neighbor, and in a minute or two I'll ask someone, or hopefully someone raises their hand and tells me how you do it. They should know, yeah. So Charmy is saying you all know because he showed it to you.
But I'm not looking, so.
Cool. Does anyone want to tell me how it works?
Add mean and multiply by scale.
Mm-hmm. That's correct. So you draw your sample and then you multiply it by the scale, and then you add the mean. That's exactly what you do. And in terms of, do I have the code for this, or do I have, no, I have it on the next. Okay, the code comes in a couple of slides. I should have really put it on this slide because I motivated through code, I'm sorry. Let's go back. So does everyone understand why this is the case? So you can go through the mathematics and show that if you look at the expectation of this quantity here, it's going to be 0, and if you look at the standard deviation, it's going to be 1. And then if you do it here, if you take the expectation, this goes away. So the expectation of z is mu, which is exactly what we want. And then for the scale, you have to do a bit more massaging, but basically, if you compute the scale or the variance of this object, then it just gives you this thing squared, which comes out of the computation of looking at the expectation of z squared, basically. But if you haven't, so typically I think you do this in some probabilistic machine learning courses, but maybe not in all of them. So if you haven't seen this before, I'll put in the reference in the slides that I'll share later on about this, and you should all go through this because I think it's very instructional. And so what does this mean now for our expectation? So you can take this kind of initial expectation that we had that was where the z is sampled from down here. And then using this trick that we just had where we express it in terms of sampling something standard that doesn't have parameters, and then we move it around and scale it, we can say this is the same thing as taking an expectation with respect to the standard normal and then having the parameters inside of the argument of the function. And so if we do this here in the estimator, we see we use reparameterization in the same way. So here's the expression on the left that we try to compute the gradient of. We re-express it by sampling from the normal and then moving the dependence inside of the argument of the function here. And now if we take a single sample estimate, the sample comes from the standard normal that we don't care about and don't want to optimize anything on because it's just the standard normal. And the dependence lives in here. And then our autograd system is happy and can take gradients through it because it's just inside of the function that we're trying to optimize. And it's not in the sampling procedure anymore. And that's kind of the reparametrization trick that got introduced from the Kingma, I guess, in their paper. And something similar was also done in the kind of second reference here for variational autoencoders. And I think I don't like thinking about it a trick because I think trick always assumes it's something hacky or something that you shouldn't really do. But I think this is actually something very practical that you do, and that's why I put trick in quotation marks. Yeah, and so now you can take the gradient because the gradient now lives inside this object that's still directly with the gradient, and you don't have to kind of take gradients into anything that's here on the right. Right. And reparametrization is actually something much more general than the reparametrization trick, and you can do it with many different objectives, many different distributions, not only with Gaussians. And typically, it allows us to take something that is called a score function gradient, which is an object like the one I write here in the top, and turn it into something that's called a pathwise gradient. And a pathwise gradient is something where the functional dependence has moved inside of the argument of the function. And typically, there's no guarantee, but typically in machine learning, pathwise gradients, so the ones after reparametrization, have a lower variance than estimators for the score function. But there's no guarantee. And not all of the distributions can be reparametrized. And then there's different tricks on how you can deal with them, like implicit reparametrization. And all of the main or major probabilistic machine learning libraries, like Distrax, for example, it's just one for JAX that I keep using, but I think for PyTorch there's also some, and there's also TensorFlow probability, but I don't think TensorFlow is this common anymore. They do the sampling and the reparameterization for you. So for example, if you implement a VAE in JAX, then you would sample from a normal distribution where you say, this is some mean parameter and some scale, and then I want to sample through it. And then under the hood, it does all of the reparameterization for you, and I can just take gradients through it. And I don't need to worry about doing the rescaling and everything myself. But if you wanted to implement all of this in NumPy, then you would have to be careful and do this, because otherwise you can't take the gradients or can't compute the gradients. And there's a really, a really great review paper that came out in JMLR in 2021 that I think is probably also 100 pages long, and Google would probably also say it's a book, most likely, that explains all of this in this context, but in many, many, many other contexts as well. And I think if you're interested in kind of this, so it's quite mathematical, but I think it can be quite instructive and kind of debunk some of the myths in some cases and explain why things happen in a certain way. I think this is a really great resource to have a look, and you don't have to read all of the 91 pages every evening before you go to bed. You can look at them once, or you can also only look at some parts of them. Yes?
How we can be sure that it is a good estimation, and if we are not, why do we actually take all the scale from -1 to 1 to normal distribution, right? Why we don't use something smaller to make sure it is a better estimation?
So I guess that kind of goes back to here as well. So the question was, why do we... So we might be interested in something that happens around the mean, is your argument. And why do we actually sample and not just take the mean, for example? Or why do we not just take samples a little bit around the mean? And the answer to the question is that wouldn't give us the right answer, because you then would sample from a different distribution. Because you are interested in outliers. I mean, outliers can give you a lot of variance, but you're interested in kind of unbiasedly estimating the expectation. And if I ask you, what's the weather like tomorrow, then you can't really tell and say, it might rain, it might snow. It's very unlikely, but in principle, I guess it could happen. I mean, you could say it's raining, or it could be very windy, or maybe not very windy. The average would always be, it's like a little bit windy, and probably around this time of the year here in South Africa, the sun will shine. So the mean prediction would always be the sun shines. But that prediction isn't always correct, because sometimes it rains and sometimes it's very windy. And you want to be able to say, yes, mostly it's going to be sunny, and mostly I'm going to pick something that's close to the mean. But sometimes I'm going to have these outliers, and these outliers are also important because they actually cover the whole distribution. So that's the reason why we do that. And it introduces more variance, but it means it is unbiased. And we can trade off bias and variance. We can say, okay, I'm going to reduce the variance by only sampling things close to the mean. But then my estimator will be biased and will no longer be a true estimate of what I care about, but it will be kind of biased in some way. And sometimes you can bound things. And then it's maybe a lower bound or a lower upper bound or something that you can still optimize, but something that might be uncontrolled, it could be larger, and then you get something that's larger than the log probability because you've now changed what you're actually optimizing. Does that make sense? Cool. Any other questions? No, great. Then, okay, so now we put it all together. We're almost done with writing down how we actually optimize things. So we started with the elbow, looks like this in the top, or equivalently, just the thing inside the bracket for one data point. So we don't have to carry around this expectation over the data all the time. And then the thing that you actually optimize or implement in practice looks something like this. So in this case, I've also sampled the KL divergence. So the KL, as you know, was this expectation over Q of log Q over P. So you have the log Q over P, and if you use the product rule of logarithms, you can pull them apart, so you get log Q minus log P. And that's all evaluated at a sample Z that we've drawn from the approximate posterior by using the parametrization. And I told you in some cases we can also compute the KL divergence in closed form, which means, so this is an approximation of the KL where we use a single sample that has the same expectation as the expression if we use it in closed form. And it can have larger variance, but in some cases we can't use the closed form expression. And in some cases it actually turns out that using the sampled expression, even though by itself it has larger variance, together with the estimator for the likelihood here on the left, combined we might actually have lower variance. And that's just an empirical thing that you find sometimes. But I wanted to have an objective where I just use a single sample. So that's this, but equivalently this could be just the KL from above. Okay, so now how do you train your VAE? We have the objective, we have the reparametrization, we have the picture with the encoder and the decoder and the nice cat is back. Okay, so what do? You sample a mini batch of data, then you sample some of the randomness, you use the encoder to find the mean and the scale by kind of encoding the image or the batch of images. You multiply it with the epsilon and mu width so that you get a sample from the Z, which then is basically here in the latent space. And then you use the decoder to decode this, and you get your likelihood term, and then you can put in the image and ask how likely is the cat under the likelihood term that I computed. And then you can evaluate the loss and take gradients now because we use reparametrization both with respect to theta and with respect to phi. And then you can use the gradient in your favorite stochastic optimizer like SGD or ADAM or LMW or whatever you want to use. And then that's how you optimize your VAE. And later on, once you've trained it, and if you want to adapt the encoder to new data, then you do exactly the same thing. But you have to really make sure that you don't touch the theta anymore, because the theta has been trained on the training data, and we can't train that on test data because that's the model. But the phi, which are kind of the things that happen in the encoder, are fine, as I explained to you earlier, to be optimized to test data. But you really need to make sure that you only optimize those and you freeze the parameters theta. And yeah, so the encoder step basically happens in computing this latence, and the decoder step that happens in evaluating this likelihood term. And just to say, this is the code for kind of reparametrizing a Gaussian. If you have a different distribution, then you have to, then this term will look differently. Yes, question?
So the output of the decoder is to be a Gaussian, right? So both output, the theta of the cat will also have variance?
Yeah. Yeah, so here I wasn't really sure how to draw a cat and its variance. And so I put just log p of x given z, but it's exactly what you say. It's the mean and the variance of the cat. And then to compute basically the loss term, I take the cat image on the left, which is really just an image, and I ask how likely is it under this mean and variance Gaussian.
Could you also train it just having the cat as an output?
So what you can do, and I think that's then getting even closer to an autoencoder, is you say, I'm going to fix the scale of the Gaussian, and then it's not a learnable parameter. There's still a variance, but I don't learn it. And then basically the things that you optimize very much look like an L2 loss, basically. Because you're not caring about kind of all of the other terms in the Gaussian, and you know the log of a Gaussian is basically like an L2 term plus things that depend on the variance. And if the variance is fixed, then you don't have any gradients, so in terms of optimizing them, they go away, so it's just an L2. So it's like mean squared error, basically. If you had a Bernoulli, then the Bernoulli doesn't have a scale, it doesn't have the probability vector, so it's just a single output, basically the mean, but there's like the variance of a Bernoulli is fixed and determined by the mean as well, for example. Any other questions? Yes?
So here we are training simultaneously theta and phi. So
Yes.
what's the impact of asymmetrizing the learning rates, or like making, for example, the encoder kind of optimal with respect to current decoder?
Yep. So there's lots of different schemes. There's also this quite old wake-sleep algorithm, which I think comes from, I don't want to lie, but I think it's from Jeff Hinton, right? Wake-sleep. And then there's wake-sleep for similar algorithms like this, where basically you say, I'm going to freeze so it's a bit like EM, basically. So you first only learn theta parameters, then you freeze those, then you learn phi, and then you freeze those, and then you learn theta again, and you go back and forth. So you could do that. That's an approach. You can have different learning rates for the two. We know that in GANs, you have, you train the decoder, like the generator for X steps, for 3 steps, and the discriminator only for 1 step or something, or the other way around. I don't train GANs usually, as you can tell. I think people in the VAE literature, just to compete with the GANs, because our images didn't look as nice, we can say, oh, but it's very stable, so you can just use this, it always works, you don't need to care about all of these details. If you make the model more complicated, there can be cases where you can get better results by all of these tricks, but typically they're not necessary. And because there's a lot of hand tuning and so on, you try not to touch it too much. But if you want to, you can invest time in it, and typically it will improve results slightly. There's also hybrid schemes, for example, for the inference, where the parameters phi, you would first have an encoder, and then you can still optimize them as if they were just distribution parameters. So optimize the mean and to make this amortization gap a little bit closer. And there's like iterative amortized inference schemes for that, for example, or iterative refinement schemes. So you can always use more compute in order to do that, but typically this is good enough as a first order approximation to get started. And then if something doesn't work or doesn't work well enough, then you can try, there's like a whole zoo of literature that basically explains you which part you can touch and how you can maybe improve the optimization.
Is there any consequence on the structure of the latent space?
The latent space will always look a bit differently, I would say. And it always depends, like you have initialization affects it, how you optimize it affects it. I don't think there's something general you can say, but there will be differences, definitely. Cool. Any other questions? Okay, then let's continue. Okay, so before we kind of go to I show you some results with VAEs, and we move on to hierarchical VAEs. You might say, hang on a minute. So we started with this intractable objective that we couldn't compute, which was this log p, where the integral was inside, or the expectation was inside the logarithm. And then we ended up with this new objective, which is the elbow, which I tell you is more tractable. And indeed, the expectation is now outside of the logarithm, so that's good. But we still have to sample. From Q. We can't kind of compute it in closed form. Why didn't we use like MCMC samples or MC samples in the very beginning and just sample from the prior and evaluate this objective? And I already gave away half the answer, but have a think about. So we still I should use the laser pointer more. In this objective, we do have to sample from Q, which is sampling which kind of problems. We could also have sampled here, without going through all of the mathematics, introducing an amortization network, doing all of these things. Why are we using the elbow and why are we not using Monte Carlo samples just up here? Anyone? Any ideas? Think about it briefly.
Because of expectation under logarithm.
Yeah, so expectation logarithm is one thing because we. So the answer is correct. Expectation logarithm is one thing that the estimator wouldn't be biased. Wouldn't be unbiased because if we did it up here, if you do the expectation with a single sample, then if you took an expectation of the whole thing, including the logarithm, and you asked, is my estimator unbiased, then the answer would be no, so that's one problem. It would be a very, very loose bound though, so you could still optimize it and it would still be a bound because it works pretty much like the elbow where you move out the expectation. So it uses kind of Jensen's inequality, you can make an argument. It's still a bound, although it's a very loose bound. So expectation is one thing, and then, or bias is one thing. What is the other thing I talked about in estimator that can be problematic? It's not a trick question, I just want you to think about it. So an estimator has two properties. It has the bias, and what was the other one? Someone has to shout out. Variance, very good. The problem here is that the variance can also be very large of this first term. And the reason for that is credit assignment. Because we saw earlier that if you sample from the prior, you're sampling from this huge space. And the xn here is this cat image. And the cat image has like a small concentrated posterior somewhere in this latent space. And so the probability of you sampling something in this prior space and then decoding it and it giving you exactly this cat image or something very close to it is very, very low. Which means typically the likelihood you find will be 0, which means the log likelihood will be almost infinite because the prior just doesn't cover, like most of the space of the prior doesn't explain the cat very well. And so this not only is this biased, but it also has a huge variance because typically it's infinite and sometimes it gives you a finite value. And that's why we need the encoder, because the encoder does the credit assignment for us and it tells us which region in the latent space is like most likely to explain this cat, and then we only sample from that space. And that gives us something which is much lower variance, which is also why a single sample estimator typically is enough. Cool. Then let's have a quick look at some of the kind of architecture and modeling choices. So we already talked about the prior and the decoder. And then similarly, for the approximate posterior, you can use a Gaussian, which I've been using, and it was only diagonal. You can use a full covariance Gaussian. You can again make it a mixture. You can use a normalizing flow, and I think that will be what Steve Cronin will talk about to you on tomorrow and on Friday. And then the other question is, so that's the distributions. What neural networks should we use, and what kind of different choices do we have? And there's many, 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 many different choices you can use. So typically, people started out with making the encoder and the decoder both feed-forward neural networks that are just fully connected, so MLPs. They could be convolutional, which kind of makes a lot of sense with images. But you can also have autoregressive models. You can have many, many other things as well. Then the latent space can be just a single vector. So basically, you have a vector that describes the image. Or it can be something that's spatially arranged. So it's a vector, but it's arranged as a matrix, and then kind of the bit in the top left explains part in the image that are in the top left, and the part in the latent space on the bottom right explains the image on the bottom right, basically. And this is what's sometimes called convolutional or spatially arranged latent space. The decoder can be an MLP, it can be autoregressive, it can be convolutional, and the prior can be fixed. So it can just be a standard normal, but in some cases they might also be parameterized or they might be conditional as well. And any combination of these, so you have 2 to the 4 different things, is at least one sequence of papers, I would say. So if you go into the literature on VAEs, there's basically all of these combinations will be found together with, I think, a combination of everything that we saw on the previous slide with the different distributions. So there's a lot of literature, and hopefully what I explained to you about VAEs allows you to take a paper and then see how it fits into kind of this type of description. Very quickly, how do we evaluate VAEs? So if you want to look at numbers, because people in machine learning look at numbers and then say, my numbers are better than your numbers, what is the number that people in VAEs look at? they look at the elbow bound either, but the elbow bound can be very loose and kind of optimizing it and so on can be problematic. So many papers report something that they call log P. But we already know log P is not computable or is intractable. And what they actually mean is that they compute something which is called an importance-weighted estimate, which is that instead of taking one sample, you take many samples, and then there's a weighting scheme that tells you if it's a sample that's useful or a sample that's useless in some sense, and then you weight them accordingly. And it gives you an estimate of log P that's tighter than the elbow. So this is kind of the theorem in this paper, and that's the importance-weighted autoencoders by Buddha et al. Paper from 2016, where basically the more samples you take and you use them in that scheme, the closer you get to the true likelihood. And I think someone in the break came up and asked me about like a guarantee for how tight you can make the elbow to the true log P. So you can use importance sampling to get closer and get a feeling for how much you improve, but also you have the guarantee that if you use infinitely many samples, you'll get log P. But how quickly that converges, I don't think that there's a guarantee for that. There might be some estimates of the convergence rates and so on nowadays, I'm not sure. But you can get close. And people in practice use either 1,000 or 5,000 samples, so that's actually quite a lot if you want to evaluate. But it might not be enough to make it really tight. And the other thing I should have probably told you is that there's something that's called AIS, which stands for annealed importance sampling, which is something that Redford Neal came up with in the 2000s. And that's a scheme that's basically an importance sampling scheme that uses transition probabilities and is quite complicated, but actually can give you a very good estimate of log P, and then you can probably also use that to estimate how good the bound is. But that's also get tricky to implement and can take a while to run, and so people typically just use this importance sampling estimates, and that's good enough. And remember, the Q in this distribution here can always be optimized at test time if you want to really get out the last bit in your table, but I don't think that kind of optimizing these things for tables is kind of the way to go, but it's one approach. Right. So some use cases for VAEs. I already said we use them for dimensionality reduction and compression, or for representation learning, where you try to disentangle different dimensions and have meaningful interpolations in this latent space. And I already showed you this picture on the left, where you see a head from different angles or different speaker identities depending on how you move in this latent space. Similarly, you can also do this with other objects, or with colored faces and so on, where basically one dimension is the identity of the chair and the other one is how the chair is rotated, how big the chair is, what type of leg the chair has, and so on. So you have all of these different dimensions that basically get found by the model, and that you then can play around with. But it always usually works within limitations, and it's never going to be a pure Euclidean latent space that kind of you can say I'm going to do vert to vec type, king is to queen as mother is to father or something like that. That typically is difficult, and there's a lot of tricks to kind of make it work a bit better and find these dimensions, but it has its limitations. Another one you can do is missing data imputation. So you have the original images on the left, you have a mask that corrupts the image, and then you can ask, please fix this, and it works decently well. Another interesting use case that's nothing to do with images is molecular property prediction. So in this case, you build an unsupervised model of molecules. So you take a molecule up here in its SMILES representation, and I think SMILES is like some feature that the people use for molecules. Then you have an encoder that takes the SMILE representation and embeds it into a continuous latent space, and molecules are something that's very discrete. And then you find that the network in the latent space arranges the molecules in some structure. And then during training, you also kind of decode them, and you again get back your SMILES representation. But then later on, this latent space is structured in an interesting way, and it has molecules that have similar properties are similar to each other in this latent space. And so now you can build a classifier or a regressor on top of that latent space for known molecules where you know the properties to give you a property prediction. For example, is this a poisonous molecule? Should I eat this or should I not eat this? Will it be a good catalyst for something? So all of these properties you can predict. And then you can also move in this latent space by saying, I'm going to start out with that molecule, and I want a bit more property of that molecule, what happens if I move in that direction. And then you see that your classifier basically gives you properties, and you can start searching in this latent space, which is continuous, where you can do optimization, whereas in the discrete space of molecules, you can just add or remove molecules, which is a discrete problem, which is combinatorial and much harder. And so this was I think this and similar approaches in biology is why for example, VAEs are used a lot in kind of these topics. Another cool application is in dynamics modeling, or is one example where basically you have kind of these little points, the 3 points, and they're moving dynamically in some space. And you want to have a model that basically predicts the dynamics of these things. And so what these researchers here have done, they took the images, they're encoded, both in terms of a position and in terms of a velocity, and then you embed them in a latent space, and then you learn a dynamical system which is very low dimensional because the initial images are very high dimensional. The position and velocity encode to a very low dimensional space, and then you can learn an ordinary differential equation that describes dynamics in this latent space. Then you evolve the system in latent space, and at the end or throughout, you can kind of decode the images again. And then you see that here in the beginning, it's reconstruction, and then you extrapolate to kind of further along in time, and you see that the balls keep moving according to what you would think they should be moving like. So this is like another example where VAE is used as a small component block. And I think nowadays VAEs are always used as like small components block in like a larger system. But there's also failure modes of these very simple VAEs, and I don't really want to hide those because I think they can be problematic as well. So for example, you have very limited capacity and expressivity of kind of the base model with the Gaussians and everything that I described. So if you take, for example, the CIFAR-10 data set, which any GAN can fit, and all of the diffusion models can fit, if you just take a simple convolutional VAE with not so many layers and Gaussians, those are the best samples you can get, and they don't really, I mean, CIFAR never looks really like something, but I mean, this looks even less like CIFAR. And then there's other problems. For example, there's a thing called posterior collapse in terms of the optimization, which means that some of your latents might be completely uninformative, and the posterior collapses to the prior, which means that this KL in the elbow becomes 0 for these dimensions. And that means that the output then doesn't really depend on that latent vector anymore because there's no information in that because it's the same as the prior. And you can think, there's 2 points of view on this. There's a positive view which says, well, this is automatic complexity control because it tells you we don't need all of the latents. So that's, in a way, you could say it's good because it tells you the problem is even lower dimensional than you thought. But the negative point of view is that you're wasting model capacity because you told the model, explain these images and don't throw away resources, and you don't really do a good job at explaining this. So collapsing here is not the right choice. And sometimes all of the dimensions can collapse and the model can't explain anything. And that's mostly an optimization issue, but it's something that can unfortunately come up in practice. And then there's many tricks to mediate that. Furthermore, sometimes the training and optimization can be difficult because we already said you have the encoder and the decoder and you both optimize them. And it basically means like you're trying to hit a moving target in the optimization because the encoder tries to fit the decoder and the decoder tries to fit the encoder. And because both are moving, that can be problematic. And then something like an EM-style algorithm that we discussed earlier can, for example, be a remedy to stabilize this. And the big problem in general with likelihood-based models, and that's also why GANs, I think, were quite successful for a while, or I guess still are, is that the simple likelihoods that we keep using don't actually accurately capture what we ultimately care about in terms of visual quality or maybe for some downstream tasks. Because for Gaussian, you say everything should be close to the mean, but it's fine if it's a bit different. But ultimately what it means, it cares a lot of like the little imperceptible details where I think if every pixel in an image was off by 1 out of 255 pixel values, as a human we would be very happy about it, but the likelihood would be very unhappy about it. And so what we think as like how an image looks good and how should we measure distances between images and how should we assess the quality of an image, that's basically what it means to choose a likelihood. But we can't really encode that information in the likelihood because we don't really know how we measure these things properly. And so that's a big problem with likelihood-based models in general, and VAEs also suffer from that. And then the disentanglement sometimes works and sometimes doesn't work, and I think there are tricks to make it kind of work, but it's not not a stable property. And if you keep retraining models, then sometimes it finds the disentanglement and sometimes it doesn't. So just to summarize, VAEs are kind of one standard probabilistic model for unsupervised machine learning and dimensionality reduction, where we cannot optimize the log likelihood, but we derive this lower bound, and we used amortization and the reparametrization trick in order to make it trainable and then work with it. And so now we have some time for questions, and afterwards I'll tell you about hierarchical VAEs, and then next lecture we'll talk about diffusion models. Are there any questions at this point? We had some questions in between, but if there are some questions now, then we can do that before I move on to hierarchical VAEs.
Any questions at this time? Okay, in that case, let us break then for tea. And
No, we I still have 15 minutes, I think.
So this is just a short break for questions. Okay.
Yeah, this is just a short break for questions.
Okay,
Yeah.
okay.
Sorry.
So when I saw the questions, I thought that was yeah.
No, that was the intermediate questions before we get to the end questions. Because I usually tend to forget to ask, and so I need to put these in more as a reminder for myself than for you. So this was the little exercise about KL divergences, where you saw very quickly the solution now, but we unfortunately have to move on, and then if we have time in the end, we'll look at that. Or you can look at it at home when you look at the slides. So hierarchical variational autoencoder. So far we looked at VAEs that had a single latent variable, which means it was like it could have different dimensions, but it was like a flat vector or something that's spatially arranged, but something that didn't have any structure on its own. And we saw that can have limited modeling capacity, especially if we move to larger scale data like CIFAR, or, I mean, CIFAR is no longer large scale, I guess, but ImageNet or beyond that. And one property of this large scale data, especially in the image domain, but also if you look at video or audio, is that it has a very clear cause to find structure, because you have like, if you draw something yourself, you don't start in the top left and then draw, but you kind of draw the outline and then you refine it a bit and then you keep adding details to it. And the model can't really do that because the model has a flat vector, and the flat vector has to explain everything at once. So in a way, the model it can't really build up the image part by part. And the idea is to kind of now structure this latent space hierarchically so that some part of it can be responsible for the coarse detail and some part of it can be responsible for the finer detail. And then if you look at the diagram for that, it could, for example, look something like that. So this would be a 3-layer model, and you see there's lots of arrows going on here. The important bit is that the space is structured, so the prior P of Z now is a prior of different dimensions. So for example, in the picture on the right, it would be D equals 3. And typically it's structured in the sense that in itself it's a small model that factorizes in some way. So for example, it would be you independently draw the variable Z1, then condition on Z1, you draw the variable 2, and so on. And that could be, for example, in the top, you draw, I don't know, in the top, you draw the rough outline, and then you add more details, and then you add more details. That could be one way to think about this. And there's lots of arrows, and that means there are a lot of choices you have to make with this model. Typically, the prior is assumed to be top-down in the sense that in the top we have the coarse detail, and in the bottom we have the finer detail. But then when you come up with the amortization network or how you do inference, there's many, many different directions. And typically people always, or like in the beginning, people always did something that was bottom-up inference, and we'll get to that. But you can make it top-down, or you could make it to go both ways. Which means that, like in factorizing the distribution, which variable depends on which. Can be top-down, bottom-up, or both directions. But remember, inference is credit assignment, and credit assignment with a single latent was difficult. And so now here we have many levels of latents. And so you can say lots of latents means credit assignment is an even more difficult problem. So in these types of models, it's usually quite tricky to get them off the ground because all of the different latents might compete to explain different bits of the image and might not agree that I'm going to do the coarse outline and you're going to do the fine details. So nudging the model to do that is not easy, but it's something that people have come up with ways of doing, but it can be a tricky problem. And then one thing that can happen in this case, if they can't agree, is that the lower level latents explain everything like traditional VAEs and the upper ones are not used. And so it's kind of your responsibility as a researcher to take these neglected latents and give them purpose. And so, as I said, typically in the very beginning, people did bottom-up inference, where the model was top-down. So you have Z1 informs Z2, and Z informs Z3 informs X, and maybe there were some skip connections. And inference was bottom-up, so X informs Z3, Z3 informs Z1, Z2, and Z2 informs Z1. And then maybe there were some skip connections, and the skip connections somehow play into it, or like defeat the narrative of this cost to find, because if everything can see the input, then the cost to find doesn't make as much sense anymore. But that's kind of one way to think about it. And because of the challenges that I mentioned before, if you just write down an architecture like this and try to train it, it will be very difficult on an optimization level. And the naive hierarchical VAE is limited to very few stochastic layers for that reason. And then over the years, people have developed more and more techniques and architectures and structures in order to make it work. So there was the ladder VAE and kind of the improved VAEs with inverse autoregressive flows papers in 2016 that did parts of that. That introduced something which is top-down inference that I'll talk about in a minute. There's BIVAR, which stands for bivariational approximate inference, I guess. That came out in 2018 that solved some of these problems. And then in 2021, we had two papers, one from NVIDIA and one, I think, from Rothschild was at OpenAI at the time, I think, who looked at two very, very deep VAE architectures that actually work very well in images, but are also quite complicated in their own right. So ladder VAEs did the following. On the left, you have a picture of how the top-down, bottom-up inference, top-down model on the right and bottom-up inference on the left, how it used to be, and which I said was limited to very few layers. And then in ladder VAEs, they said we should have inference running in the same direction as the graphical model itself. So inference should also be Z2 inform Z1, because the core structure also for inference should inform Z1. But then you somehow need to get all of the information from the inputs there. And so what they did is they introduced something that's called a deterministic backbone in a sense. So it's something where you have just a feed-forward network that has no stochasticity and no stochastic layers, that just takes the input and gives you representations at different spatial resolutions. And then you can feed them into your different latents and then basically run the inference top-down. And if you look at the graph of what they did, so I think I have colorful boxes. Yeah, so in orange is basically their model, and in red is kind of the naive model. And you see the red curve on the right, adding one layer helps, but then if you add more layers, the optimization is so difficult that it actually gets worse. But adding more capacity to the model should never get better. Should never get worse in principle. Like you could always say, just don't use them and just use the first two. But somehow the model isn't able to do that properly. And so it actually gets worse again as you add more layers. And then when you add this kind of deterministic structure, at one or two layers is not much better than the naive model, but then it kind of keeps improving as you add more capacity to the model. And then you can have tricks with batch norm and without batch norm and layer normalization and so on. And then you get all of the other lines as well, but that's kind of the rough structure. And then jumping ahead to 2 years ago now, where we have the very deep VAE that came out. So that's a thing that has, I think, about 50 stochastic layer depending on the data. And you see that I was barely able to fit everything onto one slide. So you have an image of another very cute cat that you embed. And this is, again, a completely deterministic backbone where basically you have a feed-forward network that's like a big ResNet that takes your image, feeds it for many ResNet blocks, and extracts features. And then there's some sort of pooling, and then it generates features at different spatial resolutions. And then the generative path here on the right is top-down, and it starts again at a small resolution and then scales up in a sense. And so you can think of it when you have a small image of 4x4, then you do the coarse outline, and as you scale that up, the coarse outline becomes bigger, and it's still very coarse, and then you add more finer details as you go down. And then each of those blocks here on the left is actually a whole residual network, and then top-down, you have a residual block, which is a residual network, And you also have a part that informs the posterior here on the left and the prior here on the right. So the prior and the posterior are kind of closely coupled in some sense with lots of weight sharing to make sure that they align with each other in some sense. And here is the stochastic bit happening, which is kind of what the thing that we parameterized in the past. So it's sampling. I'm sorry that's a bit small, so I'm going to explain it. You have the Z basically that you sample, and you sample it either from the posterior if you train the model, or from the prior if you just want to generate. And then that feeds into this kind of backbone that goes top down and adds more and more features over time, basically. Okay, and so that's writing down the model. How do we train the model? We still use the same elbow, and the log likelihood term doesn't look very different. It's still pretty much the same. But the KL term now looks more different because we have all of these different layers. And we have a prior that's factorized in some way, and we have a posterior that's factorized in some way. And the shape of this KL depends a lot on the structure. So for example, if you have top-down inference and top-down model, then everything lines up, and you can kind of compute the KL for each layer, so to say. But if they go in different directions, then things can become quite complicated. But there's typically always a way to do it, but computing it can be quite tedious, and you have to come up with a scheme to do it. Which is also why top-down inference is why many people like it, because it kind of factorizes into these layers, and you can say, well, the KL of all of these layers, if I have a top-down structure like this, where Z1 informs Z2, Z2 informs Z3, and so on, means I can factorize it in this way that I can write it as a sum over the KLs of the different layers. But all of these KLs now no longer have a closed form solution, but you have to estimate them exactly like I said by saying log Q minus log P. And then you also have to come up with lots and lots of different tricks to make it work and stable. So you have, as I already said, top-down inference and deterministic bottom-up path with certain skip connections. And where you put the skip connections and how you do it is actually important. Then you have this weight sharing in the top-down path that's important. And then one thing that was very crucial in this paper, where they put a lot of work in, was a careful initialization scheme to make sure that the credit assignment in the beginning kind of makes sense. And there's a whole theory of like signal propagation. If you have a deep network, how you initialize it so the signal doesn't blow up, but it also doesn't go to zero, but it kind of roughly stays stable. And they use kind of ideas and inspirations from that to make training here more stable. And then all of the tricks that people have looked in for GANs, people in VAEs are normally a bit more primitive when it comes to implementations, which is why we optimize everything jointly. And we don't know about like the cutting edge optimizers that much, and we don't use all of the techniques like gradient clipping and gradient skipping and skipping this update if a certain thing happens. But people in the GAN literature have been very good at this, and I think people in this paper looked at this type of literature and brought a lot of these tricks into VAEs as well, and they do also help in this case. And then you also need a schedule that basically schedules how this KL divergence is weighted. So I said there's a natural weighting between the KL and the reconstruction that basically is this trade-off between explaining the data, but only use as few latents or as minimal latents as you have to. And initially, when the credit assignment is bad, it can mean that you don't explain anything. And if you don't explain anything, it's really hard to recover from that. And so people have come up with lots of schemes on how you weight the different KLs, which means that, for example, each layer gets a certain number of bits that it can use to explain something without having to pay a punishment for it initially, and then you only slowly punish the model if it uses too many latents. And you have to think carefully about all of this and make it work all together, which is why this was a big engineering effort, I think, to come up with this model that then works so well. And so here are some samples from this model. So these are from, I think, CELB AHQ, I guess, or other some of the other phase data sets. Which one is it? I don't remember, but it's from another, those are not celebrities, so I guess it's not CELB AHQ. So you get really, really good phases which kind of can compete with GANs in terms of the quality. And you also have cool tricks that you can play by looking at which part of the hierarchy is informed by the image and which parts of the hierarchy samples from the prior, because you kind of can start doing mix and match type things. And then you either get something that reconstructs an image perfectly here on the right, or you get something that only has some of the features but then gives you kind of a generic face around it, and then you can kind of go between the two by sampling at different layers and so on. So that's quite cool in terms of moving things around. And then you can look at these big tables with numbers, and then you find many of these models that I mentioned before. So you have pixel CNN, you have the ladder VAE, you have inverse autoregressive flows, there's something called flow plus plus, you have BIVA, NVAE, and then the very deep VAE is the one with the best numbers. So it says ours, but obviously I'm not the author. The author is down here, on child. And so you get something that is really good also in terms of visual quality when you compare it to GANs. But if you look at the FID score, which is I think what GANs look at, because GANs can't compute, because GANs are implicit models, they're not likelihood-based models. So they can't get any of these numbers here on the right. But you can compare in terms of FID, and there I think GANs and diffusion models are still a bit better. But these models have kind of taken over. Or these kind of deep models I think are now used quite a bit in the VAE literature, at least if you care about images. If you care about like small scale data, then you won't be able to train such a deep model. And I just wanted to give you kind of a flavor of what's out there in terms of the literature. Are there any questions about the hierarchical VAEs? Yes?
I saw that in the very deep VAE, there are some residual connections from the encoder to the decoder. Is that right? Or I am not interpreting correctly the picture?
Yeah, I didn't explain the picture in enough detail. So you mean these arrows here?
Yes.
So these arrows go into the Q, but it's basically the Q of X, Q of Z given X. So that's the information from X that feeds into the Q.
All right.
So it doesn't go into, if you go, hang on, if we go,
It doesn't go into the probabilistic model.
it doesn't go into the prior. So the connection that comes from the side is this one here. So these connections here correspond to connections here. And they only go into the Q, but unfortunately it's printed very small. And the prior, which is the generative model, is here on the right-hand side, and there's no connection from that into the prior. But a very good spot, and these are exactly the things you need to look out for, because sometimes if you train a VAE, you get perfect reconstructions, and the KL is 0, and then you realize that accidentally you had a small link where all of the information didn't have to go through the latent, but it went through something else, and then you cheated, and hopefully you catch it before a reviewer does. So if you get 0 KL and perfect reconstructions, then something you should look at your code again. All right. Any other questions? Yes.
You discussed mostly pictures and images.
Yep.
But I saw that there is a transformer in this table.
Yep.
So maybe you can explain something. Is it possible to work with text as well, to get some superposition or to get some dimensional reduction for text?
So I'm sure there will be some VAE models that look at text. I'm not really aware of them, and I think that the architecture doesn't really lend itself to text, but I guess you could have some components that might be useful, I would say, but I'm not really aware of any text models. Xavi talked a lot about audio and video as well, so that's something that's happening. The molecules and all of the other, there's discrete things. I think there are also people who try to learn Gaussian process kernels with a VAE, where you embed the kernel into the latent space and then you try to do optimization in that space to do model selection for Gaussian processes. I'm not aware of language because I think language is a very difficult problem, and language also has a kind of its own field, NLP, that has very good results, and I don't think you would easily match. Also at the time when VAEs came out, something that happened in the language domain in language. And here the transformer model, that's an autoregressive model, so AR here stands for autoregressive, and that's basically a model that explains a pixel given the previous pixels and then decodes an image pixel by pixel. So it's very slow, but it's kind of a sequential problem, which is why transformers work. And vision transformers you could also use here. Any other questions? Then let me just set the scene for my next lecture, which is asking the question, do we really need to learn amortized inference? Like, there are all these problems with the encoder. Sometimes it collapses. You have to think about it carefully. Gradient computation is difficult. Do you actually need to do all of this? We saw credit assignment is hard. You have to try to hit a moving target. But we saw we need the inference network in order to train a VAE, or do we? And so one idea could be just fix the inference network, and then training the model becomes much easier in the sense that it then becomes a supervised problem, because you just have to undo the generative path just has to undo what the inference network did. in a sense. And that kind of then leads towards diffusion models and what they do, because you can think of diffusion models in some way as a VAE where you fix the encoder to do something specific, and we'll talk about that tomorrow. Cool, thank you very much, and if there's any questions, then just come up.